Once an art, but now increasingly a science. A skill pioneered by Britain more than a century ago. The manufacture and application of steel in quantity. Steel today is one of the cheapest, yet strongest of metals. And it's the most versatile. It can be worked into almost any shape we want. Its composition and treatment can be varied to give it the properties we need. It can be adapted to meet the demands of our changing technology. But first, what is steel? How is it made?
Well, it all begins with the iron ore that we dig out of the earth. Iron ore is iron combined with oxygen, iron oxide. This represents iron oxide in its most common form. 2 atoms of iron, 3 atoms of oxygen. What we need to start with is iron. Somehow we must get rid of the oxygen. To do this, we introduce carbon and burn it to form carbon monoxide gas. Here it is. At extremely high temperatures, the preference of the oxygen for the carbon increases. It breaks away from the iron and joins the carbon to form carbon dioxide. Eventually we'll have the iron, as we want, on its own. In principle, this is what happens in a blast furnace. But unfortunately, the process isn't quite so simple. This represents blast furnace iron. You see that some of the carbon has become intermingled with the iron. We've lost the oxygen, but we've picked up carbon. It is a significant amount of carbon, together with other elements from the ore, such as silicon, manganese and phosphorus, that gives blast furnace iron its properties. Here's a sample. I'll show you how brittle it is. Compare this with steel. Steel is not only strong, but also tough. To convert the iron into steel, we have to purify it, get rid of most of the carbon and other impurities. First, we heat the iron to a temperature of about 1650 degrees centigrade, and then we introduce oxygen to remove the impurities by oxidation. This is the science of the steelmaker, to reduce the carbon content to a very small and precise amount, to give us the steel that we want.
Steel. Its story begins, as we have seen, with iron ore. Iron is the 4th most common element in the Earth's crust. Much that we use comes from the broad plains of Lincolnshire and North Hants. Still more is imported from Sweden and Africa, Canada and South America. To extract the iron from the ore is the purpose of the blast furnace. Feed in the prepared ore, with limestone to combine with the impurities. Add coke. The coke provides the carbon which liberates the oxygen. And in this furnace, smelt them together with a high-pressure blast of tremendously hot air. Run off many of the impurities in the form of slag, a useful byproduct. And from the base of the furnace, tap the iron to flow into ladles. you analyze a typical blast furnace iron, you find it contains about 4% carbon, 0.8 silicon, 0.06 sulfur, 0.4 phosphorus, 1% manganese. To convert iron into steel, most of the carbon and these other elements must be removed. Most steel in Britain is made by one of three processes. Here, molten iron is being charged into an open hearth furnace, still the most common process, but progressively being replaced. The LD converter. This is a more recent method, though converter ancestry goes back over 100 years to Bessemer. Thirdly, the electric arc furnace. Its basic charge is not molten iron, but steel scrap. But whatever the charge, scrap or molten iron, or a combination of the two, the principle in steel making is much the same. To remove impurities, add limestone again. Inject oxygen through a lance and blow. Oxidize the impurities. Burn them out at a temperature of 1650 degrees centigrade. Then, when the chemical analysis and temperature are precisely right, tap the steel. A typical mild steel analysis shows that the carbon has been reduced from 4 down to 0.15%, and other elements are present only in small, controlled quantities. First iron ore into iron, then iron into steel. Raw steel by the ladleful.
But before steel can serve a useful purpose in all the diversity of its applications, it must be shaped. First, it's cast into the form of an ingot. Work the ingot down in a primary mill into a slab or a bloom. Then roll it again, or draw it or forge it into 100 more usable shapes. more than a mere metal, the very fabric of our industrial life, vital to every field of human endeavor.
Because of this vital role, a thriving, go-ahead steel industry is essential to our well-being as a nation. And never before has it been more alive to improved techniques and the need to adapt itself to the demands of technological change. Today, our tools are not so much the shovel and tongs as the computer and the electronic circuit. Take steel making itself. The need today is for speed and precision in the face of a large number of variables and ever-changing conditions. Feed in the target specifications, the weight and the chemical makeup of the steel you want, and the computer does the rest. From stored experience, it calculates the ratio of molten iron to scrap. And the amount of lime and oxygen needed for the blow. The computer is a valuable tool in what is today a complex process of rapid chemistry.
Control, cast change on number 3.
From this room is remotely controlled the making of steel in the biggest electric arc melting shop in the world. There are 6 furnaces. Each one produces over 100 tons of steel every 3 hours. Number 4 furnace is at the beginning of the cycle. It is ready to receive its charge of scrap. Number 5 furnace. Melting is about to begin. The computer calculates and controls the power settings necessary to melt the scrap. The power surging through the cables in this melting shop is enough to supply a large town. By controlling the settings for each furnace, the computer keeps the total electrical load within a preset limit. Number 6 furnace may be ready for tapping, but there is only one way to be certain that the steel is on specification. Take a sample and analyze it. The need is for maximum accuracy in a minimum time. The tools are a vacuum spectrometer to separate the elements in terms of light waves, and a computer to measure and interpret the results. Within 4 minutes, the analysis is transmitted. Carbon 0.26%, sulfur 0.042, phosphorus 0.018, manganese 0.319, nickel 0.19, tin 0.027. When the steel is correct to the specifications, the furnace can be tapped. Automation, electronic data processing, making the production of big tonnage steel faster and more efficient than ever before. And there is the promise of something faster still, the revolutionary process of spray steel making. Take molten iron, but this time, pour it through a ton dish into a reaction chamber. With jets of oxygen and powdered lime, atomize the stream into a fine spray. and the steel making is instantaneous. Spray steel making is still in the research stage, but the aim is instant steel in continuous production. From continuous steel making to the continuous casting of steel, a shortcut process already established. Feed molten steel into water-cooled molds. Control critically the rate of flow. And you form steel in the shape of a slab, or a bloom, or a billet, directly and continuously. The benefits are obvious. This single process does away with the intermediate stages of ingot casting and primary rolling. New techniques, new efficiencies for the production of steels in bulk for a wide variety of uses. But today, special steels are required to meet more rigorous applications. Steels that won't fatigue or fracture under stresses undreamed of only a few years ago. Tonnage steel making, as we have seen, is concerned with burning out, oxidizing unwanted elements. But to make a special or alloy steel, take the chemistry a stage further. Add precise quantities of nickel, chromium, molybdenum during refining, or while tapping to give the steel the properties you want. But if you take a sample of this steel and study it closely, probe it and analyze it microscopically with an electron beam, you discover minute imperfections. These non-metallic particles could result in fracture under severe stress. They're mainly caused by the presence of oxygen and other gases during melting. To reduce them, the steel is degassed in a vacuum. There are several methods. Here, the molten steel is drawn up into a vacuum chamber. The gases are released, and the degassed steel returns to the ladle. Repeat the cycle until every single drop has been exposed to the vacuum. Another method, vacuum casting. Ladles of steel direct from the furnace are teamed through a vacuum chamber, where again the unwanted gases are removed. The result is a 200-ton ingot of extremely high quality steel. Magnify a sample of this steel several thousand times and compare it with the same steel before degassing, seen here on the left. You find that most of the imperfections have disappeared. Steels as clean as these give a very high performance as bearings or generator rotors. But for the cleanest steel of all, there is another method. It is called vacuum arc remelting. First, suspend a specially shaped ingot of conventional steel in a copper crucible. In the crucible, create a vacuum. And with the intense heat of an electric arc, remelt the ingot from the base. 12 hours later, when the whole of it has been consumed, remelted, and degassed drop by drop, you reveal a new ingot. A pure, clean steel. A steel for the space age. New processes, new techniques, new steels. The pace of development has never been faster. And look at the exterior world of steel. This too has been transformed. Now clean lines, clean air. An industry keenly aware of the need for a healthy environment. An industry increasingly science-based and automated. Unrivaled in the opportunities that it offers in production and engineering, in research and administration. You start with an order. Process it through a computer, along with 100 others, into a production schedule. Iron ore to iron, iron into steel, steel into slab. Now the slab will be reduced, stage by stage, through half a mile of the most sophisticated rolling equipment in the world. A journey controlled electronically. British Steel, progressive and challenging. The underlying strength of our future prosperity as an industrial nation.